Previous lectures we predicted the acidic strength based on pKa values, whereas lower pKa value means a better acid or a stronger acid. Now we are going to do all this based on the qualitative approach, not quantifying it. Just by looking at the structure or the stability, we will predict the acid strength. For this, just see that if there is an acid, a neutral acid like HA, and it reacts with a base B negative. Most of the acid-base reactions are equilibrium reactions. So this base takes up this H positive and an anion is generated. So BH plus A negative, which is the conjugate base. So this is acid, this is base, this is the conjugate acid of base, and this A negative is the conjugate base of acid HA. So focus on this A negative. So this more stable this conjugate base is, the more stable this conjugate base is, implies stronger acid HA. And it makes sense also because things or the reactions happen because they want to attain a state of more stability. Okay, so if HA on losing a proton becomes more stable as A negative, so that equilibrium will be favored as compared to if A negative is becoming HA and becoming less stable. So I repeat, the more is the stability of the conjugate base of the acid, the better or the stronger that acid is. Now, how to see or how to evaluate the stability of the conjugate base? For that, there are various factors. So we will first see the thing which is called electronegativity. Electronegativity is basically a tendency of an atom in the bonded state to withdraw the shared pair of electrons more towards itself. So suppose there is a molecule AB. So if B's tendency to withdraw this shared pair, there are two electrons, one is coming from A, one from B to form a covalent bond. And if B's tendency to attract the shared pair more towards itself is more, we say that B is more electronegative than A. Okay, so it is basically the tendency to withdraw the shared pair of electrons. Now let's see with an example, we will see how this factor can help us in predicting a stronger acid or a weaker acid. For this, let's take the example of, say, ethane. Okay, so when ethane, so if I write this in the expanded form, CH3, and there is a base, suppose there is a base B negative, okay, and it takes one of the protons, and what you get is CH2 negative. So this base takes any one of the protons because all of them, they are equivalent, so any one can be taken up, and this is what you get. Okay, so this is one reaction. And if I compare this ethane plus base reaction with ethanol, and there is a base, so this base, suppose, takes up this H, and what you get is CH3, CH2, O negative, fine, plus BH. So a question may come to your mind that why I am selectively abstracting this proton by a base. It is because this proton is connected to oxygen, which is an electronegative atom, which means that oxygen's tendency to withdraw the electron pair more towards itself is more as compared to if I compare this with any other proton, say with a proton like this or this. So they are connected to carbon, and carbon and hydrogen's electronegativity is almost similar, but there's a big difference in the electronegativity of oxygen and hydrogen. So this shared pair of electron is more towards oxygen, so this hydrogen is just hanging loose, so any base can come and abstract that easily. Okay, so now we have two reactions, and now let's compare them, like which one is a stronger base based on the stability of the conjugate base. So if you look at this and compare it with this, the negative charge in the case of first reaction, that is present on carbon, okay, while in the second case it is present on oxygen. And we know that carbon is less electronegative than oxygen, okay, than oxygen, which means carbon cannot accommodate the negative charge on itself in a better way. Oxygen can better accommodate that. Why? Because its tendency is like that, its nature is like that, it is more electronegative, it's more hungry for electrons, greedy for electrons, so it can better accommodate a negative charge as compared to carbon, which means that the species which I have highlighted in green is more stable as compared to the one with the yellow. Okay, so which means that the second equilibrium would be more towards the product side as compared to the first equilibrium. Okay, so the equilibrium 2 would be more towards the right hand side, as compared to equilibrium 1. Why? Because in this case the negative charge is coming on carbon, which is not which cannot that easily accommodate the negative charge. Fine, we can take one more example. We can take the example of, so this was when the atoms, they differ in their electronegativity, and we can easily predict, and both of carbon and oxygen, they belong to the same period. If you can, lithium, beryllium, boron, carbon, nitrogen, oxygen, and all. So carbon and nitrogen, they belong to the same period, and as we move in a period, the electronegativity increases. That's a very straightforward thing. Okay, now if we have like negative charge on atoms which belong to different periods, in that case how are we going to work? So let's take the example of equilibrium 2 with equilibrium 3. So equilibrium 3 would be like if I take a thiol or thioalcohol, you can say like this, and you have a base which abstracts the proton and generates anion. Okay, now if you are asked like which of the two equilibriums, second and third, which would be more towards the right hand side, or in other words, will the ethanol more acidic or the thioethanol more acidic? So in that case we need to compare the species which I'm highlighting in blue with the one which is in green. So in the green, negative charge is on oxygen. In the blue one, negative charge is on sulfur. And they are present in different periods. So if you look into the periodic table, so it is oxygen, sulfur. So we are moving down the column. So as we move down the column, the electronegativity decreases, which means sulfur's electronegativity is less as compared to oxygen. Okay, so electronegativity decreases down the group. But here there is another factor which dominates, and that is the size factor. Size increases down the group. Okay, so sulfur's size is bigger as compared to oxygen. And because of this, sulfur can better accommodate one negative charge as compared to oxygen. Fine. And that is why this sulfide, this anion which is highlighted in blue, it is more stable as compared to the anion which is highlighted in green. I repeat, although if we go by the electronegativity thing, Then oxygen, negative charge on oxygen is more stable as compared to that on sulfur, but here the factor which dominates is the size. Since size of sulfur is bigger, so bigger sulfur will accommodate that negative charge easily, that would be spread around it, while smaller oxygen will not be able to accommodate the negative charge to that extent, like in a better way. So that is why equilibrium 3 would be more towards the right hand side as compared to equilibrium 2. So we'll explore more about the electronegativity factor, inductive effect factor, resonance factor, how they affect the acidic strength in the subsequent videos. Thank you.